All right. Hello and welcome. I sent out a couple of emails this morning. I can't remember what the first one said, but I know that so there's a Google Sheet you can sign up for one-on-one meetings. I've got tomorrow and Friday available, and if we need to go beyond that, if we fill those up, I'll start making some time available Monday and Tuesday. You should now be able, if you have already taken the test, which is most of you, to see the items missed, to see what the correct answers are, to see what your responses were. And now, just in the past 15 minutes, I heard that the videos were not working, so I've embedded YouTube videos for each question as feedback to each question. So all you should need to do is press play, and if it doesn't work, let me know. Please don't disseminate links to those videos widely. They're currently unlisted on YouTube, but anyway. But if you've already taken the exam, you should totally have access to be able to see those things. Yeah, I think that's all I had to say about that. So we're going to finish up today, I think, with Chapter 7 and 8. We first need to deal with the stereochemical consequences of the E2 reaction. Last time we mentioned that it's a requirement for the E2 reaction for the beta proton to be anti to the leaving group. And the reason for this was that only the beta proton that is anti to the leaving group has a substantial amount of LUMO on it. And so that didn't make much of a difference back when all we were considering was, say, elimination from a primary or a secondary alkyl halide where the beta protons were all methyl groups and they were all the same. Either way, your elimination product from an E2 reaction is this alkene, and there's no stereochemistry whatsoever to worry about. However, we can easily design situations where it becomes more difficult and there are important stereochemical consequences. So, and at the same time, is that me dinging? That's embarrassing if it is. Not embarrassing if it's you guys. You guys are allowed to have your phones ding in the middle of class. I told you if my phone was on and it was Amber texting me, it would be Yoda going, not sure who else. I told you my mom is the Death Star. My brother-in-law is Chewbacca. My sister is Jabba the Hutt. I mean, it's not intended to be rude, but Boshuda. All right, so let's suppose this is our alkyl halide, and let's suppose we want to just do an E2 reaction. We'll use a sterically hindered base, good base, that is a weak nucleophile, and it is weak because of sterics, too large to attack carbon, but can attack beta protons. Now, one of the challenges here is that we've got a couple of different kinds of beta protons, which I'll draw in different colors. So in blue, we have the beta protons attached to the methyl group. Now they're all equal to each other, so I'm only going to draw one of them. So that's beta carbon 1 and beta proton 1. Then on the other side, we have beta carbon 2, and beta carbon 2 has two different protons on it, HA and HB. It may not be immediately apparent that these two protons are different from each other, but you can tell that they're different if you look down the carbon-carbon bond between the alpha carbon and beta carbon 2. So here's beta carbon 2 with, let's see, from this perspective, a methyl group would be coming out to our right. and then a proton up and to our left, and a proton down and to our left. The up one we're calling A, the down one we're calling B. Then anti to the methyl group is a CH3, a bromo is up, and there's another proton that's implied that's down. Notice that HA and HB experience different environments. This molecule does not have a plane of symmetry because the alpha carbon is a stereocenter. In this conformation where HA and HB are both close to the methyl group, only one of them is close to the bromo group, right? So two protons, and this is an interesting principle that you're going to encounter again, and if you take the Chem 353 lab, Dr. Bronson is going to just hammer this until you've got it. A CH2 group, the two protons on a CH2 group in a molecule with a stereocenter are different from each other, okay? We have a word for CH2 groups that are different from each other in a molecule that is chiral. These two CH2 groups, we're going to call them diastereotopic. Topic or topicity refers to shape. Diastereo refers to the fact that they are different. Don't worry about this term for now. I'm just introducing it because you will hear it again. It comes from the idea that if you replace one with something other than hydrogen versus the other, those two options would be diastereomers. In any case, they are different. And one of the reasons you can tell this is the case is imagine elimination from this conformation of the two protons, which is competent or ready for E2 elimination. Is it HA or is it HB? HB, why? Because HB is the one that is anti to the leaving group. That's where some of the LUMO is going to be. So if we do the E2 reaction, this arrow here represents electrons going to the space between the alpha and beta 2 carbons, and then the leaving group leaving. As that happens, as that elimination process happens, we're going to make a double bond in between the alpha carbon and beta 2. And in that double bond, notice that CH3 on the front carbon and CH3 on the back carbon are still going to be trans to each other. And then because we've removed HB, only HA is left on the beta 2 carbon, and then in the back we'd have a proton here. In other words, if we remove HB and now we go back to looking at this molecule from the side, we have just made a trans alkene. Okay, do you see how eliminating when HB is anti to the leaving group gives you the trans alkene, right? Now, is HB the only proton that on that carbon that could ever be anti to the leaving group? No, we can rotate around carbon-carbon bonds, right? So it would be actually trivial to take the carbon in the front and grab on to HA and rotate it counterclockwise. Such that HA would now be anti to the leaving group. So here's beta carbon 2. Here's HA. HB would now be, here. And the methyl group would now be here. In the back, we're leaving that carbon unchanged. So here is the bromo group, and here is the other hydrogen on the back carbon. So now a base can remove HA, which is anti to the leaving group. Again, there we're forming that new pi bond between alpha carbon and beta 2, and leaving group leaves. In the resulting alkene, the proton that's left over is HB. The methyl group on the front carbon is to our left, as is the methyl group on the back carbon. And if we were to view this from above, we would now be looking at a cis alkene instead of a trans alkene. Okay, so sometimes it's going to matter which beta proton we eliminate from, because they're going to lead to different stereochemical outcomes. Another reason that those two protons, HA and HB, are called diastereotopic is that the two products from this elimination are diastereomers. Right? One cis, the other's trans. Colton at home is asking, does it matter how favorable a conformation is in? That's a good question, and you might wonder, well, isn't this anti-conformation more favorable than this gauche conformation? And in that case, could we expect to see more of trans than cis as a result? That makes sense, though it's actually a complicated issue dealing with kinetics. It has to do with how far apart these two conformations are in energy, how fast they interchange, versus how fast each one goes to products. And so we're not going to do that we're not going to weigh the relative abundance of these two conformations, in part because interchange among them is fast at room temperature. You see another hand? Yeah.
I'm just confused from the second type of products of the leading projections, how that, I'm having a hard time seeing that translate.
Going from here to here?
Yeah.
Okay, that's fine. Maybe I drew it in a funny way, so I'll take you through how we would do this. So hover your worry dye there. These look like Charlie Brown worry marks. You guys don't know the peanuts, though. That's way before your time. It's way before my time, too. So we're looking down on this molecule from above. It would look like beta carbon is on our left. And maybe I'll use color. So here is the beta carbon. From our perspective, looking down at this molecule, and I suppose here is my nose, and here's, so you can know which direction we're looking at it from. The HA would be upward, and the methyl group on that beta carbon 2 would be downward. This is the new double bond between alpha and beta carbons. In the back, we'd have a methyl group upward and a proton downward. And that's the transalkene.
I'm not seeing like the CH3 proton on the right side. Maybe it's just the one.
It's a poorly drawn Newman projection, all right? Fine. Blorp. Those bonds are meant to be eclipsed because this is an alkene, so everything's planar. Got it now? Okay. Yeah, sorry about that. And similarly, if we have, maybe we'll just name this guy Newman, who hovers over the Newman projection. We would see CH3 here, beta carbon 2 here, HB down here, new double bond, alpha carbon here, CH3 here, and proton there. Cis diastereomer and trans diastereomer. Okay. So that's complicated enough. Now, if you were to ask which one of these would form in greater amounts, you would need to consider a few things, but actually I'm going to hold off on the answer to that question because we still haven't dealt with the fact that there was another kind of beta proton there. All right, so we've identified two products, each from a different kind of beta proton, but we now have another kind of beta proton on a totally different carbon. This is not going to be a stereochemical consequence of E2. This is going to be a regiochemical consequence of E2. What does regiochemistry mean? Regioisomers are constitutional isomers. It's different connectivity. So let's just predict the product that would form from elimination of the proton from beta carbon 1 using this starting material. Now, if your beta carbon is a methyl group, all the issues of being anti-periplanar you can sort of forget about or pretend you didn't know, because that methyl group has 3 identical protons. It's going to rotate around such that one of them is anti to the leaving group. And who cares which one? Because they're all equivalent. So a base would remove this proton, form a new pi bond with the alpha carbon, leaving group leaves, and you end up with this alkene. This is a regio isomer of the 2 diastereomers that we've shown up there. It's a regioisomer because it has different connectivity. Okay? All right, well, we got ourselves into a tricky situation now because we have 3 potential products from an E2 reaction. And we want to know, do we just draw them all? Is it possible to choose one that's likely to form in greater amounts? So to do this, we have to know something about the E2 reaction. I'm going to draw just a single energy diagram for the E2 reaction and point out that in many cases E2 and or SN2 are irreversible. Generally, you're starting with very reactive nucleophile, and so it's very difficult to go backwards from products. Here's a starting material for an E2 reaction. Here's the transition state, and here's the products. So in a case where a reaction is irreversible, the fastest product to form is the major product. Okay, great. So we know that actually this difference between starting material and transition state for the various isomers we're getting here should determine the ratio of products we get. I'm only showing you one pathway, but what I'm telling you is that it's possible that the pathway leading to the trans diastereomer is different in energy from the pathway leading to the cis diastereomer, which is different in energy from the pathway leading to the other regioisomer. So when reactions are irreversible, the fastest product to form wins. And so we need to talk about what the E2 transition state looks like. Doing this is not too bad. You have a base with a partial negative charge on it, removing the beta proton. So in the transition state, the beta proton is in the process of being removed. At the same time, we're forming a new pi bond between alpha and beta, and the leaving group is leaving. And so the transition state for this reaction has a significant significant alkene character, meaning as you get to that transition state, the pi bond is already substantially formed. Not completely by any means, but already substantially formed. And what this means for us is if the transition state is already like an alkene, then the more stable alkene product must come from the more stable transition state. So we can tie the stability of the product with the stability of the alkene character in the transition state. And therefore, the more stable alkene is the major product. Okay. So let's talk about alkene stability, and let's do this by looking at our three potential products: the cis diastereomer, the trans diastereomer, and the Regio isomer. And it's useful at this stage to maybe remind you of some language that we're going to use relating to alkenes. We're going to call this alkene over on the left, alkene or olefin on the left, a mono-substituted olefin or alkene. And the reason we're calling it mono-substituted is because relative to our simplest alkene, ethylene, which is unsubstituted, we've not swapped out any of the hydrogens for things that are not hydrogen. So our Regio isomer is a mono-substituted olefin. Both of these diastereomers are Dye Substituted Olefins. Only one is cis and the other is trans. So let's talk about the relative stability of cis versus trans. Any potential explanation you can see there? Why you might expect one to be more stable than another? Sterics, okay. Follow that up. What do you mean by that?
One side of the trans is are anti to each other, and the cis are.
Right, okay, good. In the trans conformation, the methyl groups are anti to each other, whereas here they are eclipsed with each other. So just based on the same reasoning that we've got from our carbon-carbon bond kind of conformational issues, yeah, the eclipsed conformation should be less stable than the one where the methyl groups are anti. And if you build somebody's been playing Among Us and watching YouTube. If we build a model in Spartan for the cis alkene, I think you'll be able to see the steric hindrance. So the two methyl groups are close to each other, and in fact, if we use a space filling model, you can now see they're actually bumping into each other. Whereas the trans option, the methyl groups are as far away from each other as possible and are not bumping into each other. So yeah, you've got some simple steric arguments that explain why trans is more stable than cis. And yeah, the explanation is sterics. All right. Now we need to talk about mono versus dye substituted olefins. And there's a rule you can memorize from your text, or we can understand the reasoning behind it. The rule is that more substituted alkenes, that is, alkenes where you've replaced more of those protons with hydrocarbons, more substituted alkenes are more stable. Okay. Written by the hand of God from Sinai, you can just accept that and move on. Or you can try to understand why. There's some things we don't understand why, and we're willing to accept some things on faith. But in science, you can always ask why and do experiments to find out why. And so why not, right? And the best explanation for what's going on here is your friend and mine, hyperconjugation. Yay. Now, the fact that replacing hydrogens attached to the double bond carbons, one actually word that might be useful for dealing with double bonds as we continue to talk. A carbon that's involved in a double bond is called a vinyl carbon. A carbon that's, so both of those are vinyl carbons. A carbon that's adjacent to a double bond is called an allyl carbon. You don't need to memorize that, but I'll use those terms in lectures, so just to follow along, it'd be useful to sort of know them. So, in going from a less substituted alkene to a more substituted alkene, we are replacing vinyl protons with hydrocarbons. We're introducing new allyl carbons. And look at the difference. What does the allyl carbon have that the vinyl proton lacks? Tetrahedral shape, good. And that provides us the opportunity for carbon-hydrogen bonds on the allyl carbon to line up with an empty orbital on one of the vinyl carbons. Now, what empty orbital do we have for a molecule that's an olefin? What low energy, what LUMO do we have for that molecule? Exam 1. So, yep, go to the filing cabinet. If you got your mind palace like Sherlock, you can walk down the stairs and to whatever filing cabinet and scan through it. And remember that, yes, the LUMO of a molecule with the pi bond is generally the pi star. So, we have a situation in this monosubstituted alkene where, and I'm going to draw the pi star on this molecule as though we were looking down on it from above. There's a node in the middle. There's a lobe above the plane of the page and below the plane of the page. Wave function sign changes going across either of those nodes. So, yep, that is the LUMO, the so-called pi star. Now, adjacent to that pi star, you have carbon-hydrogen bonds that are filled. And so we have this situation where we can mix the sigma carbon-hydrogen bonds from the allyl carbon with the pi star. We're going to do this plus and minus as we always have done. I'm not going to draw what those orbitals look like because doing so is sort of beyond the scope of the class. But remember that when we do hyperconjugation, what happens is the electrons in the filled orbital get to move lower in energy for the plus combination, and the electrons and the empty orbital moves higher in energy for the minus combination. But who cares, because that empty orbital is still empty. So the consequences of hyperconjugation are that the electrons from the carbon-hydrogen bond spread out and are stabilized, and that the LUMO spreads out onto the adjacent carbon-hydrogen bonds. All right, so that's stabilizing. This is exactly the same reason that more substituted carbocations are more stable. Same principle, just different empty orbital, right? In this case, it's sigma, we would call this sigma to pi star hyperconjugation. And again, we're talking about the filled carbon-hydrogen bond from the allyl carbon donating into the pi star. Okay. So, if that's the case, then the more allyl carbons we put on an olefin, the more chances for hyperconjugation we get, the more electrons get to spread out and delocalize, and the lower in energy the alkene is. All right? So the reason more substituted alkenes are more stable is because more substituted alkenes have more chances for sigma to pi star hyperconjugation. So that's your explanation why. And perhaps knowing why will help you to remember the rule and where it comes from. So what we would say in this case for the reaction I've shown you up at the top of elimination reaction of this alkyl bromide is that we would not be surprised to observe 3 products. We would expect the monosubstituted alkene to be a minor product, and if you had to choose between the two dye substituted cis versus trans, you would predict that trans should be the major product. Okay? Now, how am I going to do this on an exam? Well, I could ask you, which of the following are products of this elimination reaction? And then you could say 1 or 2, or 1 or 2, or 1, 2, and 3, or 1, 2, and 4, or 2, 3, and 4, and all of those crazy options which you hate. But in that case, you would need to just recognize the different diastereomers and or regioisomers that were possible, or I could say which of the following is the major product. And if I ask you that, there has to be a clear way to choose. In this case, you would choose the dye substituted trans alkene because of the 2 more stable dye substituted options. The trans is less sterically strained. David's question is good. Just to clarify that the hydrogens don't have to be anti to the pi bond for the CH sigma bond to stabilize the pi bond. You know, the way I've drawn it, this is a good question. The way I've drawn it, it doesn't, all we need is for one of them to sort of swing up and line up with the pi star. So yeah, they do need to line up either eclipsed or anti to the pi star. Either way, it's the same because the pi star is the same on either side of the molecule. I haven't bothered drawing it that way because it was hard to do, but yes, if you were going to look down this carbon-carbon bond from the allyl carbon to the vinyl carbon, in order to have good hyperconjugation, this hydrogen would need to line up with the pi star. The issue is, though, that the rotation is possible around this carbon-carbon bond so that it can definitely happen. All right, other questions? Yeah?
Would the isomers that you said were possible for it, wouldn't there be resonance? Or would there be?
The question here in the classroom is about resonance. Is there a possibility for resonance? Are those resonant structures of each other? No. They would be if there was a lone pair with a negative charge on that carbon, but as it is, there's no way to interchange these 2 options without breaking bonds. In other words, the connect and in resonance, we don't break. There's no way to interchange those options without moving atoms, and that's the standard for resonance. We can move electrons around, but just not atoms. So yeah, those aren't resonant structures of each other. Trans dye substituted has more hyperconjugation than the minor isomer? Yes. So does the cis. The reason trans is more stable than the cis is because of sterics in comparing these 2. All right. Other questions? Yes?
So if the monosubstituted is a minor and the trans dye substituted is the major, would the cis dye substituted also be a minor, or would they be like 1, 2, 3?
Okay, yeah, the question is, do you need to rank all 3 products? Can you actually predict that? I don't know actually how well that works. I would not expect you to rank 1, 2, and 3. What you've said sounds reasonable. I suppose when I ask for the major product, there's going to be a clear choice. Otherwise, it's not a fair question. If I were to ask for the minor product, there would need to be one that's minor-er than the others, I suppose. Yeah, more minor, less major. Yeah, so I will only ask is which of the following is the major or the minor product when there is a clear choice. Yeah.
For the Regio isomers, would it be possible that instead of attacking the beta 1 or the beta 2 carbon, that it would attack the other carbon?
Is it possible for the gamma carbon to be attacked? Notice that the gamma carbon doesn't have protons that could get anti to a leaving group. So those aren't going to be reactive in an E2 reaction. That's going to be like your basic run-of-the-mill methyl group. The pKa of that proton will be around 50. Much more acidic much more reactive are these beta protons. Others, yeah, Hiram.
What would occur if you had two leading groups that would transfer each other?
What would happen if you had two leaving groups that were trans to each other?
Like two bromines.
On adjacent carbons or on the same carbon?
Well, I was going to say on, what do you call it, allele carbons? Or just further away?
Okay, sure. So this is an interesting question. It actually allows us to bring up a pretty synthetically useful reaction. You're asking about what if we had a situation like this. Is that right?
Yeah.
Cool. We can actually make that. It's a simple reaction. You're going to learn it in chapter 10, which is like not tomorrow or Friday, but next week maybe sometime. You can actually react an alkene with bromine to get this particular molecule and its enantiomer. If you add just one, so it's a bit tricky. If you added just, say, one equivalent of base, and you'd need a really, really strong base, perhaps even something stronger than tert butoxide, an option of a base that's very strong and not a good nucleophile is this negatively charged nitrogen. It's not a good nucleophile because of solubility issues, but it is a good base because protons are easy to attack. You would do one elimination first. Based on the stereochemistry we have here, I'm just saying let's take that beta proton first. We would get the following alkene. And is there another Regio option? Sure, we could have removed the beta proton here, but I'm just showing you the major product. And it turns out that if we add a second equivalent, what I mean by equivalent is 1 mole of reagent for every mole of starting material. So another mole of sodium amide. We can actually do a second elimination reaction and get an alkene product, which is kind of crazy. And the way this works is exactly the same like an E2 reaction. A base removes the proton and a leaving group leaves. It's a little tougher to do the second elimination. So I think if you want to, you can stop here. But alkynes happen to be useful synthetic intermediates, at least in 351 questions. So knowing how to take a starting material that has two adjacent bromines, these are called vicinal dibromide molecules, and converting them into an alkyne is a useful synthetic interchange. Yeah, I'm trying to think what else there's to say about that. Stay tuned, we'll talk about that more, but I call this tandem E2 eliminations because you're doing one after the other. Okay, other questions? Yeah.
So we said that the more substituted it is, the more stable it is. But if both of those on the picture right there, if both of those hydrogens instead were methyl groups, would there be anything participating in hyperconjugation?
I'm sorry, if both of the hydrogens were methyl groups.
In the one right above that,
Um,
the one with the
above.
anti-bonding biology.
Oh, would there be any hyperconjugation from carbon-carbon bonds? Yes, they can do that too. They're not quite as good. I don't know why. It has to do with that carbon-hydrogen bonds are generally stronger because hydrogen can get closer. Or maybe it's exactly the opposite. I don't actually know the answer to that question. So you can strike from the record anything I just said about the reason why. I do know that carbon-carbon bonds can do hyperconjugation too, though. Okay. So question, we won't need to know tandem E2 eliminations until chapter 10. Well, you certainly won't need to know how to make a vicinal dibromide before chapter 10. But if I gave you this and as a starting material and I asked you how can you make an alkyne, I feel like that's a fair question because that's just two E2 reactions, one after the other. Okay, there's a final stereochemical issue about the E2 reactions we need to talk about. And this is, you can draw precursors or alkyl halides where only one stereoisomer is possible. So here's an example. It may come from your practice exam. And we're going to think about it this way, actually. Have to think carefully. All right, so this is fun. This is design me an alkyl halide that when exposed to a strong base that's a weak nucleophile would do an E2 reaction to give only this product. No other Regio or stereoisomers allowed. Okay. So let's deal with the Regio isomer issue. You've got two vinyl carbons. We'll call them 1 and 2. If this is an E2 reaction, there has to have been a leaving group that left. So we can use our favorite leaving group, which is bromide. Remember, an E2 reaction removes a proton on one of the carbons and a bromide on the other, or a leaving group on the other. So let's just for fun say that we're going to put the leaving group on carbon 2. That would put the extra proton that we just lost on carbon 1. pH, by the way, represents phenyl group. I should have said that. It's a benzene ring as a substituent to a larger chain. The squiggly line indicates that the benzene ring is attached to something. Sorry for that confusion. So without worrying about the stereochemical issue, let's think about this as a candidate for the elimination reaction. Will this give only the regioisomer shown? Thinking, why would I ask the question if the answer was yes? Well, I like good questions. Go ahead.
With the on the beta carbon and two hydrogens, couldn't you rotate around that line of
Okay, good. So the answer here in class is that you have two protons on the beta carbon. No matter what we do, one of them we're going to have, depending on what the stereochemistry is, we're going to have, removing one of them will give us phenyl groups trans to each other, and the other will give phenyl groups cis to each other. So you've got these two, again, what we're going to call diastereotopic beta protons that are going to lead to cis and trans diastereomers. So, okay, already this is a bad idea. Any other reasons why this is a bad idea? Okay, let me ask a leading question. Are the protons in purple the only kind of beta protons in this molecule? Where are the others? Ah, beware the phantom methyl group beta protons. Yes. There they are. We have another beta carbon. And so if we eliminated these, that would give us a Regio isomer with a double bond in the completely wrong spot. So that's bad connectivity. That's a bad synthetic plan. It shows that you know what the E2 reaction is, but that you don't understand all its stereochemical and regiochemical complexity. So how might we remedy that? Let's try putting the bromine on the carbon number 1. And we won't worry about stereochemistry yet. Does this fix our regiochemical issues? And if you're not sure, let's remember what the phenyl group means. I'll just draw in the benzene ring. That way you can be confident. Here is an alpha carbon. Here is a beta carbon. Sorry, I forgot. One of those is the methyl group. All right, have we got only one kind of beta proton there? Yep, we don't have regioselectivity issues. That's we've got only one beta proton, so our regiochemical issues are fine. Now we got to worry about stereochemistry, because if we get the up and down relationships wrong here, we could make the wrong isomer. So let's just say, let's put the bromine with a wedge. Now we got to figure out what the stereochemistry of that beta carbon should be. Do you hate me yet? You should. Your hate makes you strong. It gives you focus. Go ahead.
Would it be a dash for that beta proton?
Should it be a dash? Yeah, it's kind of hard to see actually here. One better way we could do this might be to put the bromine, to choose to put the bromine in the plane of the page, and then maybe put the phenyl group sticking out at us. That way it can become totally clear where we need to put the hydrogen, right? We're going to fill in the hydrogen anti to the bromine. Now, on the alpha carbon, we have a phenyl group coming out at us and a proton going into the page. In the final product, we want the phenyl group on the alpha carbon to be trans to the phenyl group on the beta carbon. So, where should I put the phenyl group on this beta carbon? Up or down? Away from us, right? With a methyl group coming out at us. That way, as this proton gets removed, as we form a new double bond here, and as the leaving group leaves, the methyl on beta and phenyl on alpha stay cis to each other, and the phenyl on beta and the proton on alpha stay cis to each other as well. Yeah?
So does the reason the regio isomer not happen is because that carbon is now a gamma carbon, not a beta carbon?
That's right. The other methyl group is now too far removed. It's a gamma carbon. It can't be anti to the leaving group. Yeah. Those protons can't be adjacent to the leaving group. So yeah, now we've got the stereochemical issues taken care of. Some of you might ask, do I have to use that enantiomer? No. If you use its enantiomer, it will also lead to this same non-chiral product. but you do have to use this diastereomer. In other words, you do need to have the arrangement such that when proton is anti to the bromo group, the phenyl on alpha is on the same side of the molecule as the methyl on beta. Okay, so that's worth considering, and as you're working on this stuff at home, try figuring out what you could do if you wanted to get the other diastereomer, the other alkene diastereomer. All right, that needs to be it. I misspoke. I think we will need one more lecture on chapter 7 and 8, so I will make the study guide 7 and 8 due not tomorrow, but later than tomorrow.